Hopefully you all can recognize a function, the function's relation in which each element in the domain, that's your input values, is mapped to exactly one element in the range, the output values. And we're going to talk more about domain and range um, in a couple of days. But basically what it's saying is that for every x value, you cannot have more than one y value. So for example, if I had x equals 2, I can't have a value up here at some positive value and a value down here at some negative value, because then it fails the vertical line test. Hopefully that phrase sounds familiar to you. So what we're going to do is we're going to look at these three examples, and we're going to determine if the graph is a function, if the relation is a function. So we perform the vertical line test, and this one clearly fails the vertical line test. So this is no, not a function. The second one passes the vertical line test. So yes, it is a function. The third one fails right here in this middle section. Doesn't matter what happens at the end. If any vertical line passes at any point in more than one point, then it is not a function. So the first and third are not functions. The second one is a function. I just want to remind you of Euler's notation. I don't know how much you saw this in Algebra 1. You should have seen more of it in Algebra 2. But we normally learn about the point xy. The very first thing you learned in middle school when you were learning how to graph a point on the Cartesian coordinate system. Euler said that y is equal to f of x, because then this allows him to name multiple different functions on the same graph. He can call one f of x, he can call one g of x, he can call one h of x, and so forth. If they all started with y equals, then how do you know which function you're talking about? So he called them functions, and he used f of x as the most prevalent example. So xy is the same thing as x comma f of x. These are equivalent. So if I give you the function f of x equals x squared plus 3, hopefully you remember how to evaluate using function notation. F of -4 simply means -4 goes in for the x. We square it and we add 3. So that's going to give me 16 plus 3, which is 19. Hopefully you guys remember in order of operations, it's not 4 squared is 16 and then make it negative, like some of you do, because if you put it in the calculator wrong, that's what it's going to give you. But hopefully you're not putting that in the calculator. F of m simply means put m in for the x. So we get m squared plus 3, not a numerical answer. Some people get a little freaked out by that because there's not a just final number answer. It's okay. We can have answers that have variables in them. F of x plus h means that we're going to take the x out and put something in its place and square it, just like we did with the m and like we did with the -4. But in this case, we're putting in x plus h, squaring it, and then adding 3. So people tend to have a little bit of an issue with x plus h. They think that it's going to be x squared plus h squared, but that is inaccurate. Remember that x plus h squared means x plus h times x plus h and then plus 3. So you actually have to do FOIL, double distributing, whatever you want to call it. So we get x squared plus xh plus another xh plus h squared plus 3. And then I can combine my like terms in the middle and get x squared plus 2xh plus h squared plus 3. And that's it. You can't do anything else. This is the final answer here. Okay. This is something that you are going to see more of once we hit AP Calculus. I can't get my little dotted line. Oh, there we go. There we go. This formula is actually part of a calculus definition. And I think it warrants taking a little bit of time to review. I just want to remind you here, since you scroll off the page, that the function we're dealing with is x squared plus 3. So this formula is broken into 3 pieces. You have this first piece, which we just did up here. We have this second piece, which is given to you here. And then we have this third piece, the h that's underneath. So this is going to be a practice in some algebra here. So f of x plus h, let me do it. Let me keep it color coded here. That's my blue. It's going to give me x plus h squared plus 3. And I'm going to put brackets around it to show you that that's just this part right here. Then I'm going to subtract f of x. Well, f of x is what I gave you to begin with. It's the original function. So I'm going to subtract x squared plus 3. And then I'm going to divide by h. So we have all those components there. I have the blue piece from the x plus h, the red piece from the f of x, and the green piece from the h. What I want to do now is I want to simplify everything and, oops, and see what cancels or combines. So we already know what this first piece is equal to. I just did it up here, so I'm just going to recopy it. X squared plus 2xh plus h squared plus 3. With the second piece, I have to remember to distribute the negative. So I'm going to get minus x squared minus 3. And then I have everything divided by h. Now, some interesting stuff should happen here. Looks to me like positive x squared and negative x squared cancels. Positive 3 and negative 3 cancels. And I'm going to give you a hint here. If you have gotten to this point and everything that does not have an h doesn't cancel, then you've done something wrong. The only stuff you should have left in the top should be stuff with h's. If something didn't cancel, let's say you forgot to distribute the negative and you had a plus sign here, then your 3's wouldn't cancel, and then you know you did something wrong. So make sure that you are using that as like a little mid-problem double check. All right, so let me recopy what we have here. 2xh plus h squared divided by h. And now there's two schools of thought on how to simplify this. Some people will go this route. They will split it up into two fractions and then reduce it to 2x plus h, because the h's cancel here and one h cancels in the top with the h in the bottom. Other people like to factor it out. So they see that the numerator has an h in common, so they factor an h out and you get 2x plus h inside. And then you can cross the h's out to get a final answer of 2x plus h. It doesn't matter to me. As you can see, they are identical answers. Both are mathematically correct. Some people just like to eyeball it from this point here and just go, oh, this h cancels with this h with one of these h's. What you don't want to do, and if I'm screaming in your ear because I tend to talk loud, I apologize. What you don't want to do is, hang on a second. Here was the original problem. I've seen this a lot. You don't want to do this and then get an answer of 2x plus h squared. That's a big fat no-no. And when you come into my classroom, you'll see the posters over the sidewall. And I you killing a kitten. You end up killing a kitten when you do a mathematical mistake like that. Okay, so make sure that we are not doing that. All right, let's see. What do we have next here? So interval notation is a way that we can write inequalities. I'm kind of jumping all over the place here because these are things that will come up over and over again, and I need to make sure that you understand them before we get into like the meat of pre-calculus. So we use parentheses. That means that the endpoints of the interval are not included. So think back to like Algebra 1, when you were asked to graph stuff that looked like this. X is less than 3. And you marked out 0 and you marked out 3. And you put an open circle on 3 and then you shaded everything to the left. I'm hoping that's ringing a bell for you guys. You're like, oh yeah, I remember doing that. So parentheses and brackets are used to represent these set. This is, whoops, I just dropped my marker. This is called set notation. A lot of textbooks will also use interval notation, and some people prefer it over set notation. So what we're going to do is we're going to talk about how to convert back and forth between the two types of notation. So again, parentheses mean that the endpoints are not included, and brackets mean that the endpoints are included. You can mix and match parentheses and brackets, so you can have a open bracket on the left and a bracket on the right, or vice versa. Interval notation does not, I cannot stress this enough, it does not represent a point on the graph, but rather a set of x values on the graph. So if I say on the interval, let's say 2 to 5, that is not the point 2, 5. but rather what that means is from x equals 2, 3, 4, 5 to x equals 5. I'm talking about this stuff in between x equals 2 and x equals 5. So anytime you see this phrase on the interval followed by something that looks like it could be a point, it's not a point. It's an interval of x values. Okay, so let's go look at some examples here. I have in this first bullet, x is between -3 and 5, non-inclusive of the endpoints. If it was inclusive, it would have the equals to part, but it does not have the equals to part. So I know that -3 and 5 are not included in the interval. So that's why I used parentheses to show the interval -3 and 5. The second bullet, the endpoints are included as indicated by the equal to signs. So that's why I have brackets around the interval. This third bullet shows an example when mixed parentheses and brackets. In this case, the left endpoint -3 is included and the right endpoint +5 is not included. So that's why I have a bracket on the left and a parenthesis on the right. It is important to note that you never, ever, ever put brackets around infinities. You can only use parentheses around either a positive infinity or a negative infinity. That's because infinity is not an endpoint. You can't say the endpoint of infinity is included. So that's why you can't ever use a bracket around infinity. Okay, so here's what I want you to do. I want you to pause the video, and I would like for you to try these two examples. And then when you come back, you should be able to check your work. Oh no! Oh, wait a minute. What the heck? Oh, there we go. Okay, if you heard me scream a few seconds ago, I apologize. I thought that I wasn't recording. If you didn't hear me scream, pretend like I never said anything. Okay, so here we go. The answers to A would be bracket -7, 10 parenthesis, and B would be -7, 10 with parentheses on both sides. C would have a parenthesis on -7 and a bracket on 10. Let me go to the next one. Okay, so this is where we're going to start to see some infinities. So I'm talking about all numbers greater than or equal to 0. Since 0 is included, I'm going to start with a bracket and 0, comma, positive infinity, because numbers to the right of 0 are positive, and I put a paren. For E, x values that are less than 5. So that goes all the way to the left to negative infinity. So my bracket, we always go left to right. So I'm going from negative infinity to 5, and I put a parenthesis around the 5 because it's not included. And I never put a bracket around infinity or negative infinity. For F, it's going to be almost identical to E with one exception. I'm going to have a parenthesis negative infinity, and then I'm going to put a bracket on the 5. For G, I'm going to have a parenthesis on the 5, and I'm going to positive infinity because I'm greater than 5. And then for H, it's going to look very similar, except it's going to have a bracket on the 5 and a parenthesis on the right-hand side. All reals, this is interesting. So think about it. You don't have a boundary to the left or a boundary to the right. So it would be negative infinity to positive infinity. All righty. There's a lot of information here. You might, I don't know if you guys can see my recording screen or not. I'm going to move it. You might want to pause the video and jot these definitions down if it looks like something that's new and unusual to you. But basically, you're talking about where the function is positive, which means above the x-axis, where the function is negative, where it's below the x-axis, where the function is equal to 0, that's where it crosses the x-axis, its maximum value, which looks like a mountaintop, a minimum value, which is the lowest point it gets, like in a valley, where it's increasing, so getting higher as you move from left to right, where it's decreasing, where it's getting lower as you move from left to right, or where the slopes of the function are negative. Concave up looks like a cup and would hold water. Concave down I say it looks like a frown. It would not hold water. Water would run right out of it. And a point of inflection is where a function changes concavity from either concave up to concave down or vice versa. For right now, those are going to be estimated values for points of inflection. As we get into calculus next year, you find a way to find exact values for points of inflection. Okay, so hopefully you paused the video, you wrote that stuff down, and I just want to do one little analysis of this graph and then we're done. So let's talk about this graph here. This is a cubic function. I can't put arrays on my graphs in Desmos, so I have to add them myself. But let's kind of go through that checklist of stuff that was on the previous slide. Where is this function positive? Well, that would be where the function is above the x-axis. So here and here. So I'm going to just label that A. F of x is positive on the interval from -4 to 0 and from 2 to infinity. So I want you to think about that. We're taking our interval notation and we're applying it to this graph. Okay, again, you can always pause the video and go back and re-look at something if you missed it. Whoops. All right, let's talk about where f of x is negative. F of x is less than 0 where it's below the x-axis. So here and here. So that would be the intervals -infinity to -4 and 0 to 2. Okay. Where is the function equal to 0? F of x is equal to 0. Well, that's going to be where the graph crosses the x-axis. So those are not intervals. Those are actual x coordinates. So x equals -4, x equals 0, and x equals 2. Let's talk about a maximum value. A maximum value. I'm going to come up here. CD. So the maximum value. Well, this is my maximum point. I know it gets higher over here to the right, but when we're talking about maximum, we're looking for values for maxes and mins. So the maximum value is actually the y value that the function gets to. Now, it looks like this maximum occurs at about -2.5, but I don't want to know where it occurs. I want to know what the actual value of the function is. And I'm going to call that 1, 2, 3, about 3.5. I'm just estimating here. By the same token, a minimum value is where you have the valleys. So that's going to be right here. And it looks to me like the minimum value is -1. The function is increasing wherever it's getting higher as you move to the right. So this function is increasing here and here. So let me say increasing on the interval -infinity to -2.5. And also increasing from 1 to infinity. All right, let's do decreasing. Oh, I don't know why I put a D. Well, probably because I was thinking decreasing. You have G, decreasing on, well, that's going to be from here, this peak to this valley here. So it's decreasing here. So that would be -2.5 to 1. And get rid of all this extra writing here. Let's talk about concave up. So right here is where the function is concave up. If I were to pour water in there, the function would definitely hold it. But if I were to pour water in here, it wouldn't. So this guy here is concave down, and this guy here is concave up. And somewhere they come to a point where it switches from one to the other, and that's your point of inflection. But let's just talk about concave up here. So let's say that this is the point of inflection. The function is concave up until it changes again. Well, this doesn't change. It's always concave up. So we can say that it's concave up on the interval from, and we're just estimating this here, about -0.5 to infinity. And it's concave down -infinity to -1/2, right? Because all this stuff over here is down. And then our point of inflection we shorten that to POI, occurs at x equals -0.5. And again, that's just an estimated value. Okay, so this is way longer than I expected it to be, and I apologize for that. But there's a lot of information here that's important. If you need to pause and go back and look at stuff, feel free to do that. We'll do some problems based on this tomorrow in class.